Hello everyone, this is Raktutpal Bora from Assam Downtown University and welcome to the video of Heat Transfer Lab. In this video, we'll discuss heat transfer by forced convection. The aim of the experiment is to determine the average heat transfer coefficient for an externally heated horizontal pipe under forced convection. So before going to the details, let us see what is convection, get a basic idea. So convection or convective heat transfer is nothing but the transfer of heat from one place to another by the movement of the fluid particles itself or the fluid molecules itself. In the forced convection, what happens is that this movement of the fluid particles is forced by the help of fan, blower, pump, etc. The apparatus which we will be using to perform this experiment is shown here. At the left you can see the control panel. At the right bottom you can see the blower, red in color, which we will be using to blow air over the surface, that is the test surface, which you can see in the right at the top of the blower, that cylindrical enclosure. Inside that cylindrical enclosure the test surface is fitted. This is the cylindrical enclosure inside which the test surface is fitted. We will measure the heat transfer coefficient of this test cylinder inside this enclosure. The specification of the test pipe is such: it is 33 mm of internal diameter and 500 mm in length. Since we cannot see the test surface inside the cylinder very properly, I have given a schematic diagram here. You can see in the schematic diagram the air from the blower blows through a valve to the enclosure inside which the test surface or the test cylinder is attached, and in the test cylinder heater is also attached, which will supply the heat to the cylinder, and thermocouple 1 and 2 are also attached, which measures the inlet and outlet temperature. Between thermocouple 1 and 2, throughout the length of the cylinder, thermocouple 3, 4, 5, 6, 7, 8 likewise is also attached, which give the temperature of the surface. This is the manometer, which is attached at the orifice or at the outlet, which measures the mass flow rate, or you can say the air volume flow rate of the air which will be forced through the test surface. Theory: the rate of heat transfer is given by the Newton's law of cooling, which is Q is equal to HA into delta T, that is the difference of temperature, where H is the average heat transfer coefficient of the surface, Q is the rate at which heat is transferred, AS is the area of heat transferring surface, TS is the average surface temperature, TA is the bulk mean temperature inside the duct or ambient temperature inside the duct. Procedure: before starting the experiment, we have to ensure that all the knobs which supply current to the control panel, which supply current to the blower, and the dimmer which supply the heater input should be in the 0 position, and the knob should be in off position, and mains should be in the off position. After that, after ensuring that, we will switch on the mains, then we will supply current, we will switch on the knob which supply current or electricity to the control panel. After the control panel is powered, we will rotate the dimmer state which supply heat, supply input to the heater, and we will adjust the voltage in such a way that it should range from 40 to 100 volt. That means we have to adjust the dimmer state around 40, 50, 60, 70 or anything likewise. Here I have adjusted the volt to 52 volt, which this indicator gives us the voltage reading, and the indicator below that gives us the current reading. After that, we will switch on the knob for the blower so that air is forced inside the test cylinder. After switching on the blower, we have to wait for at least half hour to 1 hour, half hour to 40 minutes, so that we allow the system to reach the steady state condition. Again, the steady state condition means the system variables, in this case it is the temperature, should not change with respect to time. When it does not change with respect to time, we can say the system is at steady state. After that, after waiting 1 hour, we will start taking the temperature reading, which is given in this indicator here. For getting the temperature reading of each thermocouple, that is from 1 to 8, we have to push this knob, which you can see here. If we push this knob, we will get the reading of thermocouple 2. If we push it again, we will get the reading of thermocouple 3, 4, likewise. We will keep on taking the readings after 5 to 10 minutes, so that we will see a very negligible change in two consecutive readings. That is, the difference between two consecutive readings should be negligible or very minimum, so that we can ensure that steady state condition is reached. After that, we will put on all the observation in the table that I have shown here, and we will also note the difference of the manometer head or the water head, which is the HW, so that we can measure the mass flow rate later for the calculation. Again, heat transfer coefficient is given by the formula, that is Q by A into delta T, or temperature difference, where T is the surface temperature, that is average of the thermocouple T3 to T8. TA is the bulk mean temperature, that is the average of thermocouple T1 and T2. AS is the surface area. Now, how to find out what is Q here in this case? For calculating the Q, we know that heat gained by the air is equal to the heat lost by the test surface. That is, whatever is the heat lost by test surface, it will be gained by the air. That means that much air heat is transferred from the test surface to the air. Now, heat gained by the air is given by Q is equal to MA into Cp into delta T, where Cp is the specific heat of air in this particular case, which is 1000 joule per kg Kelvin, specific heat of air at constant pressure. Ma is the mass flow rate, T2 is the temperature of air outlet, T1 is the temperature of air inlet. Now, again, we don't know what is the value of mass flow rate. To calculate the value of mass flow rate, we use the formula, that is Ma is equal to D into rho A, where rho A is the density of air, which can be calculated again using this formula I have given here. D is the discharge or the air volume flow rate, which again can be calculated by the formula CD into A into root over 2GH, where CD is the coefficient of discharge, which is 0.64. A is the surface area, which we can calculate from the specifications of the instrument. HA is the air head, that is can be calculated from the formula, that is HW into rho W minus rho A. HW is the manometric reading, the manometric head, and rho W is the density of water. From here, we can calculate the mass flow rate. We put that value in the formula for heat gained by the air, and we put the formula for heat into the heat transfer coefficient formula, and we will get the heat transfer coefficient of the test plate. Thank you.